Welcome to this explainer. I was just looking at some recent engineering data surrounding our power grids, and wow, it turns out we have a massive puzzle on our hands. Today, we're going to dive into the highly technical and frankly, totally fascinating reality of retrofitting grid-forming inverters into legacy grid-following battery energy storage systems, or BESS environments for short. It's a huge topic in electrical engineering right now, mostly because the stakes for grid stability have literally never been higher. As we push toward a decentralized energy grid, figuring out how to make brand new technology play nicely with aging infrastructure is absolutely crucial. So if you're passionate about the energy transition, the nuts and bolts of power systems, and the hidden challenges of grid stability, well, you're definitely in the right place. Let's just jump right in and unpack what's really happening out in the field.
Okay, so we constantly hear that grid forming or GFM technology is basically this magic wand, right? The idea is that it'll just instantly inject synthetic inertia into areas with lagging infrastructure. In fact, the industry narrative often paints it as the ultimate cure for weak grids. The promise is super appealing. We just drop these advanced systems in to replace the heavy, spinning mass of traditional fossil fuel plants, and boom, grid stabilized. But when you actually peel back the layers of the field applications and look at the raw data, a much more complicated narrative emerges. Especially in these complex battery energy storage system environments, we're finding out that the ultimate cure is rarely that simple. The reality on the ground shows that dropping a cutting-edge solution into a legacy environment creates real friction. And sometimes, it introduces entirely new vulnerabilities that literally no one anticipated during the initial planning phases.
Actually, the source data puts it perfectly. It highlights that forcing these new systems into existing utility-scale sites is quite literally opening up a Pandora's box of control challenges. We aren't just, plugging a new device into a wall outlet here. We're introducing an entirely different operational paradigm into an ecosystem that was never fundamentally built for it. When we talk about sites designed for older dynamics, we are talking about legacy systems programmed with a very specific, very rigid set of expectations for how the grid is supposed to behave. They rely on established, dominant signals to function. So by aggressively retrofitting modern grid-forming tech into these established grid-following sites, operators are essentially trying to force a marriage between two wildly different generations of engineering logic. And as you can probably guess, the transition is proving to be incredibly turbulent.
To really grasp why it's so turbulent, we need to look at the fundamental clash in the mechanics. Think of it this way. Our new grid-forming setups act as voltage source devices. They're like a bold conductor stepping up to the podium, actively trying to dictate the tempo and conditions for the entire orchestra. On the flip side, you have the legacy grid-following controls, which are current source devices. These are like musicians who've been trained for decades to simply listen and follow the existing beat of the grid. Now, when you put them in the exact same facility, you are essentially asking two completely different operational philosophies to govern the exact same space. You've got one system trying to actively set the rhythm, while the other is passively waiting to follow a rhythm. It causes massive confusion when the signals inevitably cross.
And because of this fundamental mismatch, power system engineers are encountering some really unexpected stability issues out in the field. Instead of working in harmony, the disparate control loops are literally fighting each other. Because the grid-forming and grid-following assets are operating on conflicting logic, they begin reacting to each other's outputs. And this doesn't happen slowly, by the way. This systemic tug-of-war can trigger severe reactions in a matter of milliseconds. Imagine one system aggressively trying to push the voltage up, while the other system misinterprets that push and immediately tries to pull it back down. The result? A highly unstable operational environment characterized by wild, rapid-fire corrections. It can severely threaten the integrity of utility-scale parks, turning what should be a robust energy storage facility into a volatile battleground of competing algorithms.
This tug-of-war manifests into three specific, highly technical bottlenecks out in the park. First up, we have phase-angle synchronization mismatches. When these opposing systems try to lock in together, subtle errors in their phase angles create immediate tension, kind of like two massive gears trying to mesh but sitting just slightly out of alignment. Second, we face severe multi-inverter harmonic resonance risks. This is a fascinating but honestly pretty dangerous phenomenon where different inverters create competing frequency ripples that actually amplify each other. It's much like crashing waves converging in a harbor, leading to destructive resonance across the entire site. And finally, the third bottleneck, weak grid stability. All of these interaction complexities are magnified tremendously when the underlying grid infrastructure is already weak. A fragile foundation simply cannot absorb the shockwaves of these fighting control loops, which pushes the whole system dangerously close to the edge. So the crucial takeaway from all this data is that the true hurdle isn't passing initial grid code compliance tests on paper. The real test is maintaining robust synchronization when transient faults actually strike weak infrastructure. I mean, let's be honest. Anyone can model a perfect scenario in a controlled, pristine simulation to get a compliance checkmark, right? But out in the real world, when a sudden voltage dip happens or a temporary short circuit violently strikes a transmission line, that is when things get messy. In those critical milliseconds, the way these fighting voltage source and current source controls react will entirely dictate whether the grid recovers and stabilizes or if the entire multi-million-dollar site just trips offline. Paper compliance simply doesn't matter if a real-world transient fault exposes the chaotic reality of these fighting control loops.
For seasoned system architects looking at this data, this lagging transmission infrastructure forces a deep philosophical debate. It really makes you step back and wonder, are these advanced control modes a genuine architectural necessity or just an extremely expensive band-aid? Are we implementing these complex grid-forming inverters because they're genuinely the optimal path forward for the energy transition? Or, if we're being completely honest with ourselves, are we just slapping an expensive algorithmic fix onto these sites to compensate for the fact that we aren't upgrading our physical transmission wires and transformers fast enough? It's a heavy question that the industry is grappling with right now, especially when you consider the massive engineering overhead and the entirely new stability risks introduced by forcing these mixed technologies together.
To wrap up our explainer and leave you with a provocative thought, we really want to challenge the specialists watching. How would you tackle this? If you've actually encountered these unexpected field issues and watched these control loops fighting in real-world environments, we want to hear from you. How would you define the top 3 essential system engineering approaches required to finally tame this Pandora's box and achieve reliable deployment? Consider the technical complexities, the harmonic resonances, and the real-world transient faults we've unpacked today, and let that architectural challenge sit with you as you navigate the turbulent future of grid integration. Thank you so much for exploring this fascinating topic and looking at the data with me today. Keep learning, stay curious, and I'll catch you next time.